Yeah. Go ahead and get your journals out, please. So now you can think about it. So yesterday, you investigated pressure and saw that we saw pressure changing, and we changed some different things. So I want you to try to think back, what are 3 things we changed to increase pressure? So when something either increased or decreased, then pressure increased. When something else either increased or decreased, pressure increased. Try to figure out what those 3 things were. Out of this flask, like you said, Vernon, what's happening to the pressure inside the flask?
Sucking it out.
What?
You're sucking it out.
I'm sucking the air out. So what's happening to the pressure in there?
It's decreasing.
It's what?
Decreasing.
Decreasing. So we would have to change this statement to decrease.
Like that ain't should work.
So when the amount of air decreases, the pressure is also decreasing. And we, who can explain why the pressure inside there would be decreasing if there's less air?
That's how you made it to be.
Okay, so what's happening to those air molecules inside here to make the pressure decrease? So there's less. If there's fewer air molecules, how does that decrease the pressure?
They're escaping into your mouth.
Okay, so I've taken them out. What can you tell me about like the collisions of those air molecules inside the flask? So they're less. Why? Because there's fewer. So if you have fewer things, you're going to have fewer collisions and lower pressure. When the temperature, what? Increased? When temperature increased, pressure increased. So what's your evidence of that? What? Okay. Everyone, like he's thinking, everyone think. What's our evidence that we saw when temperature increased, pressure increased? Okay, what about the balloon?
It started with the water and it over one time. Over the flask, so it started expanding.
Okay, so, and then what about if we reversed it? When temperature decreases, what happens to the pressure? Okay, and again, let's think about those collisions of the molecules. Why do you think increased temperature would increase pressure? They're moving around more rapidly. And so what does that do with collisions? Okay, so happening more often. Good. All right, quickly, I want to talk about 2 of the stations yesterday. How about somebody in that region? What's happening?
Pressure.
What about pressure?
Pressure's in
What? So what's happening with the pressure? It's increasing. Why?
Just the temperature.
The temperature, and what is the temperature doing to the molecules in here?
Speeding.
Okay. Anything else to add to that? Okay, and then you put it in the cold water. I don't have ice here, so we might not get our dramatic results, but you put it in here.
Boom.
And we'll see what happens. what did you see happen yesterday?
Sucked it in.
So what do you mean by it sucked it in?
Basically, it just went inside. Big.
So the balloon went into the flask, and
It's not going in.
why would it do that?
Pressure decreased.
So pressure decreased where?
Inside the flask.
Okay. Why?
The temperature.
Because it went from a steam to a gas to liquid.
Okay. So we had our steam that was filling up the balloon,
What?
and then you cooled it down, and the steam did what? And how does that affect the pressure then?
Decreases inside the flask.
Why?
The steam went away.
Because the molecules aren't moving as fast.
Okay, so the molecules aren't moving as quickly. This is, I think, about as good as we're going to get now. Okay, and what about the pressure outside the flask, or the air outside the flask? What's that doing?
It's overpowering the pressure inside the flask.
Okay. And what's your evidence of that? Okay. And is the balloon really getting sucked in?
It's being pushed
No.
It looks like it's being sucked in, but it's probably getting pushed in.
Okay, pushed in by what?
The air on the outside.
The
Okay.
pressure on the outside is greater than the pressure.
Okay, so pressure outside is greater than the pressure inside, and so we get this balloon being pushed on by the air. Good. So now I want you to tell somebody next to you, how is this similar or different to the tanker and the can that we were doing? What similarities do you see between what we did here and when we did the tanker or the can, when we were explaining what happened to the tanker or the can? I'll give you another minute, 30 seconds here. What are some similarities between this, the story we just told of this, and the tanker or the can? Michael, what's one similarity?
They both get sucked.
Okay, what do you mean by that?
Like push.
What gets pushed?
The balloon.
So we're talking about the similarity between this and a tanker and a can.
They all get sucked in.
They both expand. And I don't know. They both have steam.
Okay, they both have steam in them. Okay, that's one good similarity. What else?
They both got a balloon on them.
The tanker has a balloon on it?
They're both sealed.
Okay, they're both sealed. Good, what else?
Good.
Powered
The
what?
pressure of the air overpowered the pressure on the inside.
You should be listening to the other people, please. So the pressure of the air,
Outside overpowered the pressure of the air inside.
and what do we see on both as, like, what do we see on both where that's happening?
They get I don't know the word. They imploded.
Okay, so we see kind of an implosion. Right now this balloon kind of looks imploded. Yesterday you saw it actually go all the way into the flask like this, which is different than the tanker, right? Any other similarities between this and the tanker or the can? And we're going to go back to your group experiments you had last week now. So each group had a different experiment. We had the size of the can, we had the amount of water you added, the amount of steam produced by how long you boiled it, those experiments. And your group is going to work on taking these new ideas you have about pressure differences to explain what you had in your experiment. And so that we can all kind of be on the same page of this, I'd like us to have a common way to show what we think is happening. So if everybody could draw the top can here in your notes. You probably want to make it pretty big. Okay. And let's use X's to represent water molecules and O's to represent air molecules in our drawing. So here's our hot plate. So if I'm going to draw water molecules and air molecules in my can, where should I draw my water molecules for starting out? So where? Okay, so let's draw some water molecules here at the bottom. Okay. So we have some water molecules here in the bottom of our can. What?
Put some air.
Okay, so I heard two things. I heard put some air and put some steam. So how could I put some air?
Put some circles.
So put some circles where?
In the air.
Where?
Above the water.
Okay, so I'm going to put some circles.
Over the water too.
Should I put air anywhere else in my drawing here?
Outside.
Okay.
Is it sealed, this can?
This can is not sealed. It's on the hot plate. Okay, so I have air molecules outside my can and inside my can. And this can has been on the hot plate for, let's say, about a minute. So what else should I be adding?
Steam.
Okay, and where should I put that? How should I represent that in my model here?
Wavy lines.
Okay, so what is steam?
Hot air.
Steam is hot air. Steam is gas. What is steam made of?
Water.
Hot water.
Boiling liquid.
Okay, so let's say this is boiling. How can I represent my steam molecules here?
Oh, it's squishy.
Okay, so how would squiggly lines show me what kind of molecules the steam is? What? I want us to think about the molecules. So we have X's and O's. How can I represent steam? What?
They're together. So
A circle.
Oh yeah, you can do
X's and O's.
A cross circle and an X in the middle.
Okay, so what would a circle with an X in the middle represent?
Air and steam. Water.
Okay, so we have air and water in the can. Yeah, you're telling me we have air in the can still. We're heating that up, but we're also having steam. Okay, so we can add arrows. So good, let's start with the arrows. We're heating this up. Tell me where I can add arrows.
Going out.
So inside the can, where can I add arrows? So what's pushing? Okay, so I have air moving around inside the can now. And can anything exit or enter this can?
Yeah.
Why?
It's open.
So maybe my air molecules are leaving the can, some of them. Okay, now let's get back to this water. Is anything happening to that water as I heat it up? What's happening to it? Johnson? What does evaporating mean?
Gas.
So this water is undergoing a phase change, it's turning to a gas. So, okay, so this water can become X's up here.
Make it a double X.
Why?
So, I don't know.
Okay,
Oh,
so if some of this water has become gas, what should I do with the molecules that I drew down here of the water? Okay, so maybe for as many as become steam, I can erase that many from down here. And what else can I add to my drawing here?
Pressure.
Okay, pressure where?
Outside.
Okay, and how will I do that?
Arrows.
Okay, so we have pressure of the air molecules bouncing off the can here. We know that we have this atmospheric pressure around us that has these molecules just bouncing off of all of us. Can air get into the can?
Yeah.
Okay, so air can also be bouncing off the top of the can. It can be going in the can. Okay. What about these X's? Are they moving around?
Yeah. They're going up.
They're going what?
Up and out.
Only up and out.
Everywhere.
They're just going everywhere.
Okay, so they're also going around everywhere. But you're right, some of them could also exit the can. I have some air molecules here that aren't moving around. What types of molecules are in the can? Are they X's or O's? Are they air or are they water? What phase are these molecules in, liquid or gas, and how can you show me that in your picture? You said if it's a liquid, we're going to show them all together down there at the bottom of the can, but if it's a gas, you're going to show them moving around all around the space. Is anything exiting or entering the can?
Air.
So you said the air molecules, and some of you said the water molecules could also, the water molecules in the form of a gas could also exit the can. I want you to tell me the cause of pressure inside the can. You were just telling me those molecules inside the can were creating pressure, the air molecules outside were creating pressure. As you try to explain what happens when you flip the can over, I want you to think about those things we talked about this morning. Is the number of molecules changing? Is the temperature changing? Is the amount of space changing? I want you to describe and explain the cause of pressure outside the can, which we talked about the air outside the can. And are the pressures inside and outside the can equal? Let's go back to our picture. At this point on our picture, this can is just resting on the hot plate. It's heating up, it's boiling. Are the pressures inside the can and outside the can equal or unequal?
Unequal.
So raise your hand if you think it's equal. Raise your hand if you think it's unequal. Okay, so this can that I just have resting right here on the hot plate. Let's see, I don't have a can right here, but there's a can. Imagine there's a can on the hot plate. It's boiling. Or the pressure is unequal or equal, and almost all of you said unequal. So can somebody explain to me why you think those pressures are unequal? Yeah.
We're not outside of the can. We're not heating the outside,
Okay.
so the pressure is still the same. Inside the can, the water is being heated, so more molecules are being released faster, and the water is decreasing.
Okay.
So they're all just become steam and going faster, moving around faster.
Okay, so he has a lot of things that are related to pressure. He says we're increasing the amount of steam in there. We're heating it up. We are, I think those are the two things you said. And those are definitely related to pressure. What's our evidence that pressures are unequal? What do we usually see happening if one pressure is different than another pressure?
Something gets crushed.
Okay, so is this can that's just resting on my hot plate crushing?
No,
So what must we have to assume about the pressures here?
they're equal.
Do they equal the inside is higher?
So she said it's either equal or the pressure inside is higher. What would we expect to see happening if the pressure inside was higher?
It explodes.
So we'd probably expect some sort of explosion or that can
Expanding.
expanding.
I think they're equal
Okay, so why do you think they're equal?
because although the water is causing more molecules to create pressure, they also have the choice to leave the can. So they're not exactly staying in there causing pressure inside. So it could be evening out the pressure outside of the can by leaving.
What do you all think about that? You think that makes sense?
She's wrong. She's wrong.
Why do you think she's
I'm
wrong?
just kidding.
Okay. So do you agree with her explanation that because this is open, things can come in and come out, and so that's equalizing the pressure, even though all these things that Fabian noticed are actually changing. We're changing the number of molecules, we're changing the temperature, we're changing maybe even how much space those molecules are taking up. But because it's open, we have that equalization.
Like the balloon with the second air.
Yeah, what about it?
You know, it wants to be equal, so it goes in the balloon.
Okay, so yes, we're talking about an equalization here. This balance of the forces or pressures. So when you get this equalization, as he called it, it stops. So at some point, that balloon inside of our flask cannot increase anymore, and so it stops increasing. Or when you squish that marshmallow, like in all of them, you got to a point where you couldn't do any more, right? So what I want your group to do is get a poster, paper, and you're going to explain your experiment from last week. Like this. You're going to have your 3 cans, and you're going to show me, using our common way to represent this now, your can on the hot plate, and then your can flipped over. So let's picture, you can add like the water bath for this. And you could draw your hot plate here if you want. And so this is the top of the can, top of the can, top of the can. This would be the top of the can down here now. Okay, so for each of your cans, you had 3 conditions that you tested. Maybe you tested a little bit of water, a lot of water, and a lot more water, or you tested small can, medium can, big can. So each of you had 3 cans. And you're going to use our way of using the X's and the O's, telling me about the phases, all these things to explain why you got the results you did. What phase of matter is this in right here?
Water.
Okay.
Stove.
So maybe once it's on the hot plate for once it starts boiling, how's your picture going to change?
Here, I see X's floating up here.
Okay. So are you going to have because up here we have on the hot plate and when you flip it over, so maybe you should have on the hot plate boiling and flipped over so that you can show the changes.
So this is on the hot plate, right?
Right. So
And then,
once it starts to boil.
wait, is this when it starts to boil?
Well,
Or just on the hot plate?
What have you drawn so far?
Well, I'm gonna draw the water, the air, and
Yeah, it's when it's boiling.
So this is when it's boiling?
Yeah. And then
So-
we just drop when it's all crushed.
So how are you going to show that this is boiling?
Draw X's.
Okay, so you're going to add some more excess?
Yeah.
Okay.
And then down here will be when we flip it over, right?
Uh-huh.
Okay.
And just make sure that you're thinking about the difference between, remember when we had our picture up there, we took, when it started boiling, some of the excess came off of the water.
Oh, yeah.
And so make sure that you're showing like how you're thinking about that. Okay. So what were you changing?
We're changing the temperature of the water.
Oh, okay. So your 3 cans should be exactly the same at the top here.
Yes. Yeah.
Okay.
And that's what they are.
Okay. So you have some X's, you have some O's. What are we representing with the arrows here?
Pressure. They're moving around.
Yeah, the
Pressure.
craziness,
The steam.
the unpredictability.
Okay. So let's look at your checklist.
Oh, that's interesting.
So what types of molecules are in the cans? We have X's and O's. How about outside the can? Any X's or O's outside the can?
There's some O's, some A's.
Oh, nice.
Okay, so I don't see any
There's some O's
O's outside
outside.
your can here.
Oh, I guess I'll just put another one.
What
I just do
phases
the
of
arrow.
molecules in? Liquid or gas? What phases are they in? We have both.
Some liquid on the bottom, some gas.
Okay, is anything exiting or entering the can? What do you think?
Yes.
Is anything entering?
Same way.
Steam is what? Steam and air can do what?
Go out and go in.
Go out and in? Okay, so do we see that going on yet?
Yeah.
Well, we see one going
Everything.
out, but I didn't draw any going in.
You know, you should draw arrows.
So keep following through your checklist here. Make sure you have your everything on the checklist being shown on each of these cans. Okay, so she's drawing it. But is each can going to have the same? What's the same about each can?
They have the same amount of water.
Of what?
A lot of water.
Okay. So you're going to have the same amount of X's in each can?
Oh, yeah. I know you do, because I know.
And how about O's? Are you going to have the same amount of O's?
No, there's gonna be more air.
In which
Bigger,
cans?
the bigger the can.
What do you think about that? Why would one of your can have more O's or more?
Different size.
Okay, and so why does different size can mean more O's?
Okay.
Okay, good.
Now,
So how many X's do you have on each?
17.
17 X's, okay. I'm excited to see what you're going to do next.
Our air.
Okay.
With little circles, right?
So just have more air, the bigger the can. Some more O's.
So double
I'll do,
the first one.
yeah, I'll do the first one, I'll double it.
All right, so you're saying when you flip it over, what's going to be, again, what's going to be at the bottom of your can?
Water.
And how much water?
Less than 50 milliliters.
Less? Why?
Steam. Wait, actually, it's the same.
What? Okay, so you have 50, so you're going to have the same amount of water that's liquid here is going to be liquid here. Okay. What's going to happen to these X's?
It's going to be turned into liquid too.
Okay.
Because once it's put into the cold water, it changes its temperature, causing it to change that too.
So how are you going to draw that?
I don't know.
So
Just
maybe.
X's.
So
Because, water, steam, it should have arrows moving like this. So if it doesn't have arrows, then it's just water.
okay. But then in this one, what are all these X's going to be? The ones that are steamed in this picture.
Just water. Yeah. So basically, there's no big steam in this when you change it.
Tell me more about what's going on in this picture.
Gas are moving around and some are escaping the can because it's not sealed.
Like making sure so I feel like they're moving slowly and all that, and and over here will increase like the speed.
So why would the speed be increasing?
Because the more you heat a liquid, the more it fizzes into a gas, and it fizzes into a gas of heating. We're gonna see speed.
Okay, so the speed of the gas, is the speed of the gas changing, or is the number of gas particles changing? Or both? What do you think?
Well, like,
Your opinion is both? What's your opinion?
I think it's both too. Because molecules are being released, going out of the can, at the same time some are coming in. And as you increase like the time, molecules are gonna be moving around faster since you're heating it for a longer time.
Okay, so let's think back again to the experiment we did with the water, and we made a graph of, it went from ice to water to gas to boiling. Describe the shape of that graph for me.
it went up, side up.
Okay, so let's talk about that constant. What does that mean? What constant what?
It means that once it reaches boiling point, the temperature doesn't rise, and therefore it just starts, the gas starts evaporating.
Okay, and so what causes the molecules to speed up?
Oh, then this is some air stuff.
The one?
Why do some molecules move more quickly than others?
Because they have more space than others. Some just like bump into each other and stay in the same place. And the other ones can be in a more open space where they can move around more quickly.
So you're telling me that space is what makes something move more quickly or not quickly? But what if you are like what can two things be moving the same speed and be in different amounts of space? Okay, so you think no, what you think yes, why?
Because they're like same particles, the same molecules, so then they'll have the same amount of speed, so they just move around, but then sometimes they'll just bump into the molecules, but then it's going the same amount of speed.
Okay, so that's how we understand how molecules work, is if they're moving, like, the space isn't affecting the speed. The speed would be the same, but the space would be smaller. So you and Andrea could run both exactly the same speed, and you could run around like outside and you could run around in here. And she would be making more collisions with the classroom walls because she's just running around, right? But if you're running around outside in the soccer field, you might not be making any collisions. So the space isn't what's changing the speed. The temperature is what changes how quickly the molecules are moving. So you told me that the temperature is not changing. So do you think the speed of the molecules is changing in here? So you said that the temperature isn't changing, and we know that temperature is what affects how quickly something moves. So if temperature is not changing, can the speed be changing?
Well, if the temperature stays the same, then it will just stay where it's at. But if the temperature rises, then the molecules will spread out and start moving around the can.
So when we reach boiling, they're going the same speed because we know that once we're in boiling, the temperature is not changing. So the molecules are staying the same speed, but what you are changing is how many molecules you have in there, which you showed me here. So I want you to focus on those numbers of molecules because you know that the temperature is not changing. And if the temperature is not changing, then the speed's not changing.
I guess so.
Okay? Good. So keep showing me what's going on in your other cans.
Well, in the last one we reached this boiling point, and so therefore I would just say keep it the same as can 2 because it, or maybe less. I don't know.
That's the water at the bottom.
So now you need to show me.
Shouldn't be that much, shouldn't it?
Well, if it reaches boiling point, then the temperature is not going to change. So that means not. There was this at least the same amount of molecules for liquid to gas in can 2.
Okay, where's the line?
Look,
Put an outline there.